Extreme heat is the deadliest kind of weather on Earth. Even as deaths from most weather decline, heat-related mortality is on the rise. The very nature of extreme heat is changing. Climate change has unleashed a dramatic increase in dangerous wet bulb events. And this is when heat and humidity combine to overwhelm the human body's ability to cool itself. In these episodes, we explore how extreme heat has begun redrawing the map where humans can safely live and the dangers and adaptations facing us in this new world. 2020 was hot. In fact, it was the hottest year since record keeping began over a century ago, and climate models point towards more warming and more records. That might seem nice if you live in a cold place, but heat-related deaths across the U.S. are on the rise. We traveled to Phoenix, the hottest city in America, to take a closer look at this problem. 2020 was also by far their hottest year, with 53 days that reached at least 110 degrees. And while Phoenix highlights the grim reality of a warming world, it also exemplifies the hopeful potential of a community with no choice but to create new solutions. Phoenix has seen an alarming uptick in heat-related illness and death over the last 5 years. Stacey Champion has worked with local government, aid organizations, and houseless people to change that.
At the beginning of April, the county decided to open up these 2 overflow parking lots and push the majority of the people in the tents into these lots, and people have died. We're gonna take Marty, we're gonna go measure the temperature of these lots.
Marty is a garden card that measures mean radiant temperature, and mean radiant temperature is essentially all the radiation that hits your body from all sides, and it's the heat load that your body experiences. It is very much different from what you get from a thermometer, which would tell you the air temperature, because it incorporates the shortwave radiation, which is essentially the direct sunlight that hits your body when you're not in the shade, and that adds a lot to your heat load when you're outdoors. Mean radiant temperature is important for us here in Phoenix, because it's the main stressor when you're outdoors in the heat.
I can't hold it. Like, it's like putting your hand on a stove.
I can look that up. Mean radiant temperature is 56.
How does that strike you, knowing that we are right next to where so many people sleep?
So I'm very much concerned about people who have to live here because they don't have a home.
Over the last year, Robert Ladeau lost his housing and has been forced to do just that.
No doubt about it. It could kill you. Heat kills. Nothing we can do about it except get out of it, drink water, drink a lot of water. So here's my tent over here. It's kind of out in the middle. There is no shade out here.
So one of the misconceptions about heat illness and death is that this is only an unsheltered or homeless person problem. Heat can impact so many different people. There was a woman named Stephanie Pullman. She was in her 70s. She owed $51 on her bill. The cutoff for their disconnect at the time was $50. So in essence, she owed $1 too much, was turned off on a day that was 107 degrees and died.
During prolonged heat exposure, the human body can become dehydrated and lose its ability to sweat, which is how it cools itself. As our body temperature rises, proteins and membranes around cells, especially in the brain, begin to fail, organs malfunction, and heart muscles begin to break down. And that can stress our body until it causes one or more organs to fail, leading to illness or even death. Heat doesn't affect all of us the same. Age, overall health, and even location are all factors that can play a big role. And remember, the definition of high temperatures depends on where you live, since our bodies adapt to the climate we live in. While global warming is the underlying driver behind why places like Phoenix continue to get hotter, something called the urban heat island effect is warming cities at a much faster rate than the global average, or even the natural areas around them.
It's absolutely critical for Phoenix and other cities to be participating in the conversation around global scale climate change, but also really important to be thinking about local climate change. Urban-driven warming has been more than double the effect of global scale warming here on Phoenix thus far. There are 3 key ingredients for the urban heat island. 1, people have machines that emit heat into the environment. 2, people use different materials than the natural landscape, like pavement, asphalt, cement, and so on. And those materials absorb and release heat in a different way than natural materials. And 3, especially in cities, the geometry of the buildings does a really good job of trapping heat and then slowly re-emitting it into the environment.
And we see this effect most obviously with temperatures overnight. It's when materials of the city slowly release the heat they absorb during the daytime back out into the environment. And the effect can be dramatic.
We're talking about something like 7, 8, 9, 10 degrees Fahrenheit of higher nighttime temperatures. When we look at our daytime temperatures, which are a mixture of this urban effect and the global effect, we only see an increase of a few degrees Fahrenheit. So urbanization has been the dominant driver of climate change here in Phoenix and in many other cities.
In August of 2003, the largest blackout in North American history left 50 million people in the Northeast without power for days. With Phoenix record-breaking 53 days over 110 degrees this summer, it's not hard to imagine a blackout that can become truly catastrophic. And Arizona State professor Mike Chester worries that a larger, more deadly Katrina-like event is looming on the horizon if cities across the country like Phoenix don't address their infrastructure vulnerabilities quickly.
When temperatures go up, people crank their AC down, colder, which puts more strain on the grid. And when the temperature is hotter, hardware breaks more frequently. So aspects of all infrastructure fail more frequently. It's not, for me, a question of if it'll happen. It's a question of when the next large-scale outage will happen. If you have a large-scale blackout, we're going to see excess mortality. It's probably going to be somewhere on the order of hundreds or thousands of additional deaths.
But there's a lot we can do to prevent heat-related tragedies, and some of it is pretty simple, like increasing shade and decreasing heat-absorbing materials exposure to the sun.
We have a church here, and that has a huge parking lot. And currently there's not even a single car standing there. We have a mean radiant temperature of 150, and that's a common issue in cities, that they have a lot of impervious surfaces. Impervious means they are not penetrable by water. And they heat up a lot in the day, and they give the heat back overnight. And it makes a huge difference whether you have a parking lot or whether you actually place lawns, native nature that cool the area.
And it's not just lawns. Well-maintained public parks and green spaces help cool the areas around them. But access to these spaces is not equally distributed.
Across the country, lack of investment in low-income neighborhoods has left them hotter than their wealthier counterparts. With fewer shaded public parks, getting out of the heat in a blackout is even more difficult.
There are a lot of studies that show that wealthier neighborhoods are usually cooler than poorer neighborhoods just because they have more vegetation, more lawns that are irrigated, and that just makes it cooler in this environment. So here we have an air temperature of 40 degrees Celsius, which is about 104 degrees Fahrenheit. So it's much cooler here in the shade with all the vegetation in the surrounding. There's this push to plant more trees and provide more shade to help people in poorer neighborhoods.
So we're here in a residential neighborhood near downtown Phoenix, where some of this cool pavement has just been applied. The sun's been up for only 3 hours now. Let's see how different the temperature is of the surface between traditional pavement here and this cooler pavement. So on the traditional pavement, we're looking at 125, 126 Fahrenheit. We'll come over to this cool seal pavement, and it is 121. So the sun's been up for just 3 hours, and already we're seeing a 4-degree Fahrenheit difference in temperature between these two surfaces. That's going to grow over the day to be upwards of 15 degrees Fahrenheit by the time we get to sunset.
Black objects absorb all colors, turning the light waves into heat, while white objects reflect them, keeping them much cooler.
If we were to take an airplane and fly over Phoenix right now, we'd see many roofs that are already painted white. Some folks in the private sector have figured out that the math works. If you make your building cooler, you're going to spend less money on electricity. Let's get that, let's make that initial investment.
There are thousands of miles of roads in Phoenix and other cities that could be treated with cool pavement surfacing, as well as countless roofs that could be painted white.
So we're at Justice Center, and it's one of the better places to get out of the heat. And they have huge, huge fans. Really thankful for places like this, because if it wasn't for them, we'd be out here sweltering in the heat.
It's 34.5 degrees Celsius, which is just over 90. And it's 105 out there, so it's much cooler in here.
This is literally a lifesaver.
Nothing like water.
There's not been enough that has been done proactively. I believe that the majority of heat deaths are preventable deaths.
We're trying to think of Phoenix as an innovation laboratory. The ideas for coping with extreme heat may very well come from here out of necessity. We need to find the solutions before other cities as we head into a warmer future.
While scientists, activists, and officials strive to find solutions to living on an ever-warming planet, remember to do what you can to stay safe during hot weather. First, stay hydrated and get out of the sun whenever possible. But if you do have to be out in the heat for whatever reason, make sure to pay close attention to signs of heat exhaustion and heat stroke, such as dizziness, confusion, cramping, and fatigue. Heat-related illness can become very serious very quickly and may need medical attention. So don't be afraid to ask for help and to help others. People who are isolated are far more likely to be at risk, so when it's hot, check on the more vulnerable people in your community. The world is getting warmer and we need to look out for each other. Thank you so much for watching. If you haven't yet, check out our previous 9 episodes for more info on natural disasters, how they're changing, and how you can prepare. Thanks again for watching. See you guys next time. The 2020s may go down in history as the decade of heat waves. And as we begin to realize just how dangerous heat is, scientists around the globe are racing to find harm reduction solutions. In the U.S., a policy that caused nearly a century of problems might actually help shed light on how to cool the hottest neighborhoods. This goes much deeper than air conditioning because counting on it alone not only warms the climate, but also strains vulnerable electrical grids that power it. In 2021, when the Northwest U.S. was hit by its most extreme heat wave on record, Vivek Shandas documented something very unexpected.
So I looked at my phone, saw 111 degrees, saw 115 degrees, and immediately thought, a lot of people are gonna die.
And they did, more than 750 in the US and Canada.
We saw these large temperature differences across neighborhoods and even individual streets next to each other. That difference is life and death.
But that large temperature difference also presents a very clear path forward. In order to survive coming heat waves, we need to make the hottest neighborhoods more like the coolest ones. But why does that difference exist? And how can we change hot neighborhoods to cool them down? We'll find out and list the top 5 things that actually cool neighborhoods when it matters most. As we've shown in a previous episode, cities are warming much faster than the undeveloped areas around them. They're also growing quickly while the underlying climate is warming.
We've had a very stable weather system for human habitation for about 10 to 11,000 years. And suddenly we're seeing rapid transformation of that climate system, which translates to our daily weather. You put that together with the fact that we have more people living in cities than ever before in human history, and that's 2 trains heading right towards each other, and we're trying to figure out how hard is the collision of those 2 trains.
So to help answer this question, Vivek and his team developed mobile thermometers that could be attached to cars or bikes and taken out into the city to collect data and create detailed temperature maps.
It's a really hot day, and what I like to do is come out, get these devices set up. And so we take this, put it in the back side over here, and then I'm gonna turn this guy around so it collects the air going forward, roll the window up. It's connected to the satellites overhead, the GPS that's telling us exactly where we are, and we're off and running to collect temperatures for the day. 6 feet above the ground, 2 meters above the ground, we would think that air has had a good chance to mix, and that the hotter air would go towards the colder air would go towards the hotter air, and we would get this kind of convective mixing, which is really what kind of stabilizes the temperature.
But when Vivek drove to different Portland neighborhoods to measure temperatures during the 2021 heat wave, he found something totally different.
Well, we found a temperature difference of about 25 degrees, which is the largest air temperature difference I had ever recorded in this city. And as we started going out and systematically collecting data in these different cities, we started seeing very similar patterns. And so then the question became, what had to happen in these cities decades ago in order for these patterns to emerge? And one of the most significant things that happened decades ago was a federal policy called redlining.
In the 1930s, the federal government began a program to prevent large numbers of foreclosures in the wake of the Great Depression. Banks would create loans guaranteed by the U.S. government using a series of maps to rank neighborhoods A through D. D neighborhoods were determined to be the highest risk and marked in red. The primary criteria for risk were race and ethnicity. Black and Latinx people were considered the riskiest, but in places like Chicago, Italians and Russian Jews were considered almost as risky. Buying a home in a C or D area was difficult or impossible. In the 1970s, these maps were publicly released along with notes from the surveyors. And if you have any hope of them not being terribly racist, I'm sorry to do this, but here's Kate Mangoya with a surveyor's note.
It's from Richmond, Virginia. It's from a neighborhood that was graded C. And it says, respectable people, but homes are too near the Negro area D2. That means that the very proximity to Blackness was enough to steal an opportunity for economic growth and prosperity from an entire neighborhood of people in Richmond, Virginia.
But what does that have to do with heat today?
That means that you're kept from the benefits of home ownership. That means that you are not going to be able to maintain your property by doing things like improving drainage and making changes like planting trees. Additionally, people who are living in redlined neighborhoods, their property values were a lot lower, which meant that the taxes for homes in that area were also a lot lower. So you see things like sewage infrastructure not being updated, parks not being sited there, trees not being planted in the public right of way. So there's a really long process of disenfranchisement.
And we're still feeling the impacts of that nearly century-old policy.
It turns out that the color scheme that was set up helped to explain what was happening in terms of the difference between one neighborhood and another neighborhood. We were able to find that in looking at 108 cities across the country, 95% of them, meaning the vast majority, followed a very similar pattern to where the D hazardous neighborhoods were consistently hotter than their A best neighborhoods.
Okay, so what's the difference between these neighborhoods? This is the intersection that recorded that 124 degree temperature. That was the hottest temperature recorded during last year's heat dome. There aren't a lot of trees here, so there's not a lot of shade in this neighborhood, and you got a lot of pavement. Let's actually compare this neighborhood to the coolest neighborhood. Here it is. The coolest neighborhood with an air temperature of 99 degrees. There's tons of trees in this neighborhood, and it's surrounded by forests. So we got a lot of trees, a lot of shade. 25 degrees cooler though. 25 degrees. But I'm glad we're here. I'm glad we're seeing this in person, because it just gives us a map of what we can do in hotter neighborhoods to make them safer.
Tree cover and shade saves people's lives. It's just that simple. Whether it's a senior who doesn't have any air conditioning, or just as simple as folks that are waiting for the bus. Right now, if you see this bus stop, they're lucky because there's a big old tree there, and guess where everybody's sitting? Up under the tree. If you look down this way, there are bus stops down here, and there are no trees, right? And there are many, many, many bus stops in the city that have no trees. Where we are today is Jackson Ward, which is a traditionally African-American neighborhood. It's hot in this part of the city, and there are not enough trees, and with development, trees get taken down and little ones get put up, and so we're constantly in a battle of trying to maintain the tree canopy. And so we've planted a few hundred trees. We're watering at this point 400 trees this season.
Trees are not the whole solution, but according to everyone we talk to, planting trees, protecting existing and maintaining your city's trees is the best way to cool urban areas. Next, decrease impervious surfaces by removing any pavement that can be replaced by something else or something more efficient. Add shade structures to public places like transit stops. That could be planting trees or building roofs. Promote air convection and mixing by encouraging a variety of building heights in all neighborhoods, especially near water. and work with prevailing wind directions to be sure tall buildings aren't blocking airflow from other neighborhoods. And finally, add surfaces that cool the area, like green roofs, green walls, white roofs, and water features in public spaces. After helping discover the extreme temperature differences we've been talking about, folks at the Science Museum of Virginia went to work on transforming 2 acres of pavement on their campus into green space.
Right now, we're standing on top of a brand new 4-story parking deck that consolidated the area that we needed for our parking for our guests, allowing us to do something extremely dramatic to the former surface parking lot that we would use for that same purpose, namely de-paving it and turning it into a civic green space for us, our guests, and all of our neighbors here in Richmond. What's really special about this, I think, is that it represents, to our knowledge, one of the largest de-paving projects in the city's history. When we look at the different types of options that we have, unfortunately, parking, green space, housing, and businesses have all been kind of put in opposition to one another, when actually responsible land use allows us to take advantage of the very limited space that we do have to maximize the benefit for our neighbors and our visitors here at the Science Museum, as well as around the city. So when we think of it, parking, housing, green space, and business development do not need to be in opposition. In fact, they should be all seamlessly integrated to provide the best opportunity for climate resilience for our neighborhoods that we can provide.
Friends of Trees has been working on the issue for quite a while, and that shows just how long it'll take to reverse a century of lack of investment. What is Friends of Trees doing in neighborhoods like this to keep them cooler?
Our mission is basically to plant trees alongside community members. In our 33-year history, we've planted over 900,000 trees and native shrubs. Due to several factors like development and heat waves, we're barely maintaining. In fact, we're losing canopy in a lot of these East Portland neighborhoods where we need that canopy the most. What we do try to plant is more drought-resistant trees, because as the heat waves are coming, what we're finding is certain trees are struggling to survive. This is a climate emergency. We should be planting as many trees as possible to help kind of restore some of the wrongs of the past as a community.
Do you live in an area affected by redlining? What about our friends in Europe, Asia, and everywhere else that set temperature records this summer? What efforts are going on to protect people from extreme heat in your areas? Let us know in the comments below, and thanks for watching. The US is warming fast, but if you take a look at global climate records, it sure does look like temperature is decreasing, at least for the last 8 years. When NOAA released their new data in early 2023, it went viral, and even weathered viewers commented that this is proof that climate change is finally moving in a cooler direction. We'll unpack that in a bit, but first, let's talk about long-term trends.
The global land and ocean temperature for 2022 was 1.90 degrees Fahrenheit above pre-industrial conditions.
But not everywhere on Earth is warming at the same speed, and there are wide swings around the globe from extremely fast warming to one particularly scary area of cooling. According to a draft government report, the US has warmed 68% faster than the global average over the past 50 years. And that doesn't even include Alaska, which has warmed way faster.
Across the lower 48, the annual temperature has increased at an average rate of about 0.16 degrees Fahrenheit per decade since 1895. But that rate of increase is 0.44 degrees Fahrenheit since 1980.
So in this episode, we're going to figure out why the average temperatures were dropping over the past 8 years, find out which parts of the globe are warming fastest, and at the end, we'll call up a resident of the fastest warming county in the US to hear what it's like. Oh, and it turns out that there's an area in the US that hasn't been warming at all, so stay tuned. Okay, first, what's up with the dropping temps?
The Earth is not cooling. So here's the thing, there can be year-to-year variability. That means those ups and downs from year to year.
We all understand this on a smaller scale when it comes to changing seasons, right? We know that nature doesn't operate in straight lines. As spring turns into summer, the temperature doesn't rise incrementally every day. It might be warm on April 1st, then snow on April 8th. but no one doubts that August will be hot. And we see this with climate change too. Temperature pulses higher, then levels off, then pulses again. But choose the right 8 years to analyze and you'll see a downward trend. 2016 was 1.19 degrees above pre-industrial levels, and 2022 was only 1.07. For reference, the Paris Agreement aims to keep the global average temperature rise between 1.5 and 2 degrees Celsius. Even inside that range, we may hit some very disruptive tipping points, including the loss of coral reefs and abrupt permafrost thaw. But no one lives in an average.
Every continent in the world is warming, but the rate of change of that warm can differ from place to place.
So where is warming fastest and where is warming the slowest? There are two big picture factors at play: latitude and oceans. First, high latitudes in the far north are warming fastest, largely because of sea ice. As temperatures rise, sea ice melts, exposing dark water that absorbs more solar radiation, which causes more warming, and the cycle continues. Now, the cycle won't continue forever. Once enough sea ice has melted, this Arctic amplification will slow down and the Arctic will warm at a rate more similar to the rest of the globe. But for now, if you're farther north, you're probably warming fast. Second, water reflects more of the sun's energy than land does, and it has a far higher heat capacity. So it takes a lot more energy to raise ocean temperatures than land temperatures. That means our large continents are warming faster than the oceans. And guess what? That's where humans live. Put this together and you get this generalization. Large land masses in the north are warming fastest. Most of the Earth's land masses are in the mid-latitudes and northern hemisphere, so those regions are warming faster than southern regions. But which continents are warming the fastest? Europe is the fastest warming continent at 0.47 degrees Celsius of warming per decade since 1980, and Asia comes in a close second. Globally, there are some unusual hotspots as well. A mysterious pocket off the coast of Uruguay and Argentina has warmed twice as fast as the global average, causing algae blooms and mass die-offs of marine species. There also seems to be a similar hotspot in the North Atlantic along the coast of Delaware to Maine. These hotspots seem to be largely driven by shifting ocean currents that bring warmer water to unlikely places. Interestingly, some places are warming slower for unexpected reasons. Parts of Antarctica have slowed warming in part because of the ozone hole, and India is warming less than its surroundings because of severe pollution keeping out solar radiation. And that cool spot in the Arctic, that's caused likely by Greenland's melting ice. So that brings us back to the US. Researchers at the University of Massachusetts found that the lower 48 is expected to reach 2 degrees of warming 10 to 20 years before the globe as a whole. From previous episodes, we know that the western US is getting drier, and it turns out precipitation plays a big role in which regions are warming. Vegetation, trees, and moisture can help mitigate warming, while drought can make it worse.
But we are seeing parts of the West and the northern tier warming faster than the rest of the country. And a lot of the driver for this is that drought periods in the West are becoming more entrenched. And as regions that are dry become more dry, that means there's less moisture in the soil. And so you'll actually have higher temperatures during the day. We're talking parts of the interior Rockies, portions of Oregon, California, as well as parts of the northern tier, Minnesota, Montana.
We also know that the Northeast is warming faster than the US average and is expected to reach 3 degrees Celsius of warming when the globe as a whole reaches 2.
Higher latitudes are warming faster. Winter is the fastest warming season for the Northern Hemisphere, certainly for the US.
This means extreme winter warming all the way from Montana to Maine. One reason for this is that snowpack is melting earlier in the season. Fewer days of snow cover means more sunlight that absorbs into the ground, warming the region. We'll take a look at the fastest warming county in the US at the end of the episode, but first we wanted to know, where is warming the slowest?
If you look from the Gulf Coast to about the mid-Mississippi Valley, so sort of that south central portion of the lower 48, there's like virtually no trend in warming or cooling across that 128-year period of record.
Some scientists believe the polar vortex can help explain this anomaly. The warming Arctic has made the jet stream wavier, allowing cold polar winds to escape to the southeast, creating a cooling effect in the winter and spring months. Scientists have also connected this warming hole to periodic thick clouds and high soil moisture that help keep daytime temperatures down. And while there was no warming trend over the past 120 years, the past 40 years do show temperatures beginning to rise. So we know climate change is experienced pretty differently around the world, but it also varies from year to year. And it turns out that a big reason for the variation comes back to El Nino and La Nina.
In an El Nino year, the waters in the eastern equatorial Pacific are warmer than average, and in the La Nina year, they're cooler, and that helps to drive various weather systems across the globe. So we often use the metaphor of like being on an escalator. And that escalator is going up. And during an El Nino year, it's like standing on your tippy toes on the escalator, and a La Nina is like crouching down on the escalator. The overall direction is still up, but you're seeing year-to-year variances. And in fact, the last 3 years, we've been in a consistent La Nina, which would be sort of a cooling. And what we've seen is really kind of a leveling off, but it's keeping pace, you know, in the top 10 and close to top 5 each of those years.
So what about the future?
It is very likely that 2023 will end among the 10 warmest years on record. And if it does, then the 10 warmest years on record would have been the last 10 years from 2014 all the way to 2023. If an El Nino were to form at the end of 2023 and continuing to 2024, there is a high chance that the year 2024 could rank among the warmest years on record.
And that has big consequences, especially for regions that are warming fast, which brings us to the fastest warming county in the U.S. North Slope Borough in Alaska, home to the native community of Barrow, now called Ukiahfik. Since 1980, it's warmed 0.72 degrees Celsius per decade, significantly outpacing the rest of the U.S. We called Evan Hobson to learn a little more about what it's like living there. He's 23, a subsistence hunter and fisher and advocate for his community. His Inupiaq ancestors have lived in the region for thousands of years with a constantly changing climate, but the current rate of change is unprecedented.
Living here in the Arctic, you know, hunting, fishing, whaling, trying to survive here in the Arctic, and not really expecting that change to come so quickly. It's scary because 1, hunting is going to be different this year. 2, thinking about the future, the conditions that I teach the future generation and will not be the same as the conditions are today.
And there are concrete examples of what near 4 degrees of warming means.
All of the houses here on the Arctic slope, they're built on stilts, maybe 8 to 10 feet in the ground in the permafrost. And once the permafrost around those posts melt, then that house kind of shifts to one side, and it's hard to open doors, hard to open windows until you correct the sinking piling.
Evan does remember this from his early childhood.
But it's more prevalent now than it was then.
Traditionally, his community gets ready for the spring whale hunt in April when snow buntings arrive, but this important marker of the season seems to be changing.
Today is April 13. I haven't seen a snowbird yet. Once I see a snowbird, then that'll tell me the bowhead whales are here and they're ready to be harvested, ready to feed the people.
He told us that the bird and whale timing just seems to be out of sync, and whaling is getting less consistent.
I mean, yeah, there's beef, chicken, and pork at the store, but that's not as healthy and nutritional as fresh, locally sourced bowhead whale, muktik, and meat.
So what about where you live? Are parts of your life changing in a warming climate? Is your city warming faster or slower than average? Let us know in the comments and we'll see you next time. There's a dangerous combination of heat and humidity which is measured by a wet bulb. It's a kind of tipping point for the human body where we lose the ability to thermoregulate and things start going very wrong very quickly. We're talking about heat stroke, organ failure, death in just a matter of hours, and it's not anywhere near as hot as you might think. And as the globe warms, this unique combination of temperature, geography, and meteorology is becoming more common.
It's becoming more and more concerning because our average global temperatures are only increasing by 1 degree Celsius. But that increase in temperature allows more water vapor to be held in the air. And so not only are we going to have longer heat waves, more severe heat waves, and more frequent heat waves, but those heat waves are going to be more humid.
14 counties in the U.S. received a 10 out of 10 risk score for wet bulb temperatures in a recent analysis. We're going to look at where they can happen and the conditions that it takes to create a wet bulb event, including the highest wet bulb temperature ever measured on Earth. So stay with us. So what exactly does wet bulb mean?
So the temperature that we're kind of used to, the ambient temperature that we check on our app, when we want to know how hot it's going to be, that's the dry bulb temperature. The wet bulb temperature is the temperature that's read by a thermometer that's covered in a wet cloth over which air is passed. So it's essentially a measure of the evaporative capacity of the environment and the ability to cool through evaporative mechanisms.
So in a drier environment like here in my living room, water easily evaporates from the wet cloth, taking heat energy with it and causing the thermometer to cool. This means that the wet bulb temperature is generally much lower than the dry bulb temperature, as you can see right here. But as humidity rises, the cloth releases less moisture since the air is already saturated, causing the wet bulb temperature to rise, gradually approaching the regular air temperature.
We humans, our primary avenue of dissipating heat is through the evaporation of sweat. And so the wet bulb temperature is kind of a better index of that evaporative capacity of the environment, our ability to dissipate heat into the environment through sweating.
A recent study shows that for over 6,000 years, most of us have lived in a moderate temperature range called the human climate niche. Clearly not all humans, but we do tend to like regions with a mean annual temperature between 11 and 15 degrees Celsius. When you compare this map of the Earth's most habitable regions to where the most extreme wet bulb temperatures have been recorded, you can see that they tend to fall well outside the human climate niche. The study also found that now as global temperatures rise, this niche has begun to change in a meaningful way for the first time in human history, creeping gradually towards the poles, leaving somewhere between 1 and 3 billion people outside the human climate niche by as soon as 2070 with high greenhouse gas emissions. Now, we get a lot of comments about the Earth's climate going through cycles, and that's true. About 50 million years ago, the average global climate was 14 degrees Celsius warmer than today. But the period of major human expansion on Earth, when we went from just a few million to 8 billion, happened during a time of very stable climate. So it's worth taking note when things change rapidly. And wet bulb events are quickly increasing. Our goal is to keep our core body temperature below 40 degrees. So Tony and his colleagues at Penn State set out to find the actual wet bulb temperature where our body's systems fail at cooling our core. Their subjects swallowed a thermometer pill and got in an environmental chamber where researchers created a wet bulb event. Now, in 2010, a paper theorized that a 35-degree wet bulb was the upper limit of human survivability from heat stress. Researchers hypothesized that above this threshold, the body would lose its ability to cool itself through sweating, with core temperatures reaching 40 degrees Celsius in just around 6 hours. So those rare wet bulb events that we talked about in the intro, those were all 35-degree readings.
So over the past couple of years, we've been conducting a series of studies aimed toward identifying the upper limits for the maintenance of a stable internal body temperature or core temperature in humans during low intensity physical activity that's meant to approximate the activities of daily living. And so those studies are done in human subjects. So they're actual empirical human subject data. not modeled data. We showed that the upper limits for a stable core temperature was more like 31 degrees Celsius or so in warm, humid environments.
Below 31 degrees, they found that the human body could keep its core temperature below 40 degrees without a problem. But above 31 degrees Celsius, our ability to thermoregulate quickly breaks down.
Above these critical wet bulb temperatures, your core temperature continuously rises. And so again, we're able to calculate the rate of change in core temperature over time and predict how long it would take your core temperature to reach 40.2 degrees Celsius. And in our studies, we found that it would only take about 3 to 5 hours.
And this means that if you're caught in a wet bulb event without air conditioning, you don't have much time to act, making this tipping point very deadly.
At these critical wet bulb temperatures, it's important that we have interventions to mitigate the rise of core temperature, such as, moving into air conditioning, replacing lost fluids, cooling down with a cold towel around your neck, an ice bath if possible.
But we know that the human body gets worse at thermoregulation as we age, making the elderly far more vulnerable to heat and humidity. But extreme wet bulb events are rare, and that's because it takes really specific conditions to create them. According to climate scientist Colin Raymond, you need heat, moisture, and stability.
So in a place like Florida, for example, it's pretty hot and humid much of the time. But the reason they don't have really extreme wet bulb temperatures is because there's not enough stability in the atmosphere. Basically, what that means is if it gets too hot and humid, thunderstorms are going to very quickly develop. So sort of high temperatures to start with, a whole bunch of moisture, and a mechanism that stops that moisture from escaping the near surface that we walk around in, and then we experience high wet bulb when all those three conditions are met. There's a very sort of geographically constrained set of places that these sort of, let's say, greater than 30 degrees Celsius wet bulb temperatures are really possible with any meaningful frequency. So in terms of life-threatening or potentially life-threatening wet bulb temperatures, there's two regions that really stand out from my work and others in the world. One of those is the Persian Gulf, the immediate coastline of it, and the other is South Asia. So basically Pakistan, Northwest India especially.
Earlier, we looked at a map of the most extreme wet bulb events where temperatures reach 35 degrees, the prior theorized limit of human adaptability. But if we expand the map out to include events hitting the threshold of 31 degrees, we see many more regions affected.
You can see that most of these extreme events have happened near coastlines in the subtropics, where there's intense heat from land and humidity from warm water, both of which are increasing in a warmer climate.
It's like a rising tide lifts all boats, right? So if we're interested in a certain level of heat stress, which of course we are because our physiologies are not going to change, and those of, for example, wildlife or livestock aren't going to change either, then with a rising tide of heat stress, we are just going to expose more and more people and systems that we care about to levels of heat stress that we're not designed for.
So what parts of the U.S. are most likely to see these events? The 14 counties most at risk of extreme wet bulb temperatures are mostly concentrated around the Gulf Coast.
And if we zoom out to include counties that received a 6 out of 10 risk score or higher, the area of impact expands up to Chicago and along the south and southeast coastlines, encompassing millions of people.
Then there's a much smaller area, and that is the irrigated desert areas of southeastern California and southwest Arizona. They're very hot, just like in the Middle East, and they're also affected by the North American monsoon, so that there are situations where there can be extremely high heat stress in that area.
But what about the highest wet bulb temperature ever registered on Earth? Well, that happened at 3 p.m. on July 8th in 2003 in Dhahran, Saudi Arabia, when wet bulb temperature touched 36.5 degrees Celsius. The heat index, or felt temperature, measured 81 degrees Celsius. That's 178 degrees Fahrenheit, an almost unimaginable extreme.
So as heat stress becomes more extreme and our predictions of it become more precise, I think there will be growing understanding and appreciation of heat stress as something that's not a situation that you can tough yourself through, but a situation that really reflects a force of nature, just like a a severe storm, like a tornado or a hurricane, for example, that everyone knows one has to take shelter from it. As we start to experience things that are hotter and more humid than we've experienced, at least in the past 100,000 years, we're going to need technology or other adaptations, like just seasonally moving out of places that don't support our natural functioning there anymore.
So what do you think? As our planet continues to get hotter and more humid, what can we do to ensure the safety of our communities, especially the most vulnerable? Mosquitoes are the most deadly animal on Earth, spreading diseases like malaria, dengue, West Nile, and more. As the world warms, we know the human climate niche changes, but so does theirs, meaning they can live and infect humans in more and more places. But in the US, they aren't the most dangerous or creepy. There are dozens of pathogens that are spreading and thriving in new locations, including some very new, very scary infections that are gaining ground across North America. But which are actually worth worrying about? And what can we do to stay safe? Well, in this episode, we teamed up with MD Alok Patel from PBS Vitals to help figure it out. We'll dig into the epidemiological data to show you exactly where major threats are spreading. And we'll save the creepiest for last, as well as what you can do to stay safe outside.
Changing weather patterns does affect the incidence of this infection, and one main concern in the recent years is that not only are we seeing an increasing number, we're also seeing increasing number of severe cases.
First, mosquitoes, because the numbers are staggering. In 2021 alone, malaria infected 247 million, resulting in 619,000 deaths globally, mostly in sub-Saharan Africa. And dengue fever, although less deadly, still kills over 20,000 each year and infects between 100 and 400 million. And the WHO estimates that about half of the world's population is now at risk. And get this, mosquito-borne illnesses are actually estimated to have killed nearly half of all the humans who have ever lived. We have very effective symptomatic treatment for malaria and dengue today, with most deaths from mosquito-borne illnesses occurring when treatment isn't available. But that wasn't the case 80 years ago. Malaria was such a big problem in the US that in 1946, the federal government decided to step in by creating the CDC, which began to eradicate mosquitoes by spraying the nerve poison DDT on, well, pretty much everything. But surprise, surprise, it turned out that DDT didn't only hurt insects, but animals and people too. So it was banned in the US, but not before malaria was declared eradicated here in 1951. So why are we talking about mosquito-borne disease now?
What's going to happen with climate change is that, as well as warming and changes in rainfall patterns, we're going to see a lot of climate variability on a sort of multi-month and multi-year scales. And this kind of variability, we've hypothesized, will drive the mosquito-borne diseases to be more epidemic.
So in other words, more big periodic outbreaks. Also, many mosquitoes have developed resistance to DDT. So we asked Dr. Patel about the leading cause of mosquito-borne disease in the US, West Nile virus.
Now here's something creepy. I can't actually tell you how many cases of West Nile virus I may have seen or come in contact with, because a lot of people, in fact, according to the CDC, somewhere around 80% of people who get West Nile virus may never actually have any symptoms. And if they do, if they are the 1 of 5 people who have these symptoms, such as fever, muscle aches, chills, they may not ever know that they have West Nile virus, and they may get better on their own.
So not that bad for most of us, but potentially deadly for specific groups.
Now, in some people, especially those who are vulnerable, meaning the elderly, young infants and children, people who may have other underlying chronic illnesses, you can have really deadly, potentially neurological symptoms from West Nile as well, such as meningitis.
And we still don't have any prevention or specific treatment for West Nile. The Culex mosquito, which carries the virus, likes a wide variety of climates. So it's already been detected in every lower 48 state, with the majority of cases occurring in the central and western parts of the country. But as winters get milder and summers get longer, we're likely to see more cases in traditionally colder states further north. So West Nile is the most deadly mosquito-borne illness in the US, but probably not the creepiest. In 2016, the Rio Olympics highlighted Zika virus with 200,000 cases in Brazil and 5,000 cases in the US that year. And Zika is creepy.
Zika virus freaks me out. Based on what I've seen, Zika can cause these devastating congenital illnesses, so things that babies are born with, such as microcephaly, which literally means small head. And the babies born with microcephaly can have lifelong disabilities.
So Zika is mostly a concern for people who are trying to have a baby or are sexually active with someone who is already pregnant.
Aside from the fact that it can be spread by mosquitoes themselves, it also can be sexually transmitted.
And in recent years, the mosquitoes that carry Zika have been moving north, and models predict the more it warms, the further they'll spread into the north and higher elevations. And these species actually prefer urban areas, often breeding in small man-made containers of stagnant water like discarded tires or buckets. But in the US, there's another insect that poses an even greater threat: ticks that carry Lyme disease, which can turn into a chronic illness.
Even though cases of Lyme disease tend to be clustered on the East Coast, in the Midwest and the West Coast, we see it everywhere. Even though the CDC reports around 20 to 30,000 cases of Lyme disease a year, new estimates suggest that number could be as high as over 400,000, with countless people still having symptoms after they've been given antibiotic treatment.
That's because it can be hard to detect. And the longer it goes untreated, the more likely it becomes a chronic, debilitating illness.
Now, cases of Lyme disease usually present as kind of an ambiguous illness, usually about 1 to 2 weeks after a tick bite. It can present with fever, joint pain, muscle aches. Sometimes we do see this telltale bullseye rash. We call it a target lesion. And if someone doesn't get treatment at this point, Lyme disease can actually turn into a severely debilitating illness that can affect your organs, such as your brain, your heart, and cause arthritis. It can be devastating for people.
And ticks like warm temperatures, so the risk of Lyme disease is highest when they are most active in late spring and early summer months during warm, humid weather. But with winters getting milder and shorter, tick seasons are getting longer. And warmer temperatures also mean they're able to move further north. Over the past few decades, the disease's range has expanded significantly to include most of New England and even parts of Canada. And this trend seems likely to continue. Climate change makes some areas hotter and wetter, benefiting mosquitoes and ticks, but it makes other areas like the US Southwest hotter and drier, benefiting other, maybe creepier pathogens like valley fever. It's a fungus whose spores live in soil. When that soil is disturbed and gets into the air as dust, these spores can be carried with it into our lungs.
While most of the infections are self-limited and goes away, some patients do develop severe infections. This can be a chronic pneumonia that persists for a long time, and sometimes the infection spreads from the lungs to other parts of our body, like our brain, skin, joints, or bones. And that's when it becomes very hard to treat and control.
Thankfully, the number of cases and mortality are still low, but it can be fatal, and it's becoming more common very quickly. Arizona and California have the most cases by far, but it's not just in the Southwest. In recent years, the fungus spread as far north as the state of Washington. And models predict the area where people are exposed to the fungus will double, covering nearly the entire western US by 2095. But the last thing I want to do in this episode is discourage anyone from getting outside and enjoying nature. And even though these threats are very real, there's a lot you can do to avoid getting them. So let's start with mosquitoes. The most effective and easiest measure you can take are simply using the right insect repellent and wearing long sleeve shirts and pants, especially during dusk and dawn when mosquitoes are most active. In terms of repellents, those containing DEET, picaridin, or oil of lemon eucalyptus for those who prefer something more natural are best. And as far as ticks go, the same advice applies regarding those repellents and long sleeves and pants. And after being outdoors, conduct a thorough tick check on yourself and your pets.
Do a full skin exam. This is not just looking at the outside of your arms and your legs, but head to toe, behind your scalp, your ears, your neck, your chest, your torso. You get the point. Everywhere.
And if you do get bitten, the chances of getting Lyme disease go way down if you can remove the tick in the first 24 hours.
And to remove the tick, simple. Get some tweezers, make sure they're sterilized. You want to go as close to the skin as possible. Grab the tick and pull it up consistently and firmly. You don't need to twist or jerk it because you may actually worsen the problem. And by the way, those folklore at-home remedies, such as using alcohol or a match to remove the tick, don't do them, they don't work. The tick may actually burrow deeper into your skin, causing more problems. You don't want to do that. All you need is tweezers.
And for valley fever, if you're in a known hotspot, stay indoors during dust storms or when air quality is poor. Wet down construction sites or gardens before digging to minimize dust. Keep windows and doors closed on windy days and use air filtration indoors. And if you do have to go outside in dusty conditions, a trusty N95 goes a long way. Now, let us know, which of these diseases concerns you the most in your region? Share your thoughts or personal stories in the comments below. And be sure to go check out our friends over on PBS Vitals for the latest science on health and the human body. Thanks for watching. The last time we had the same level of carbon dioxide in our atmosphere, our oceans looked very different. But how different? I asked one of the leading experts on the subject, and what I learned was pretty shocking. The sea level was a lot higher then compared to today. That's because it takes a long time for sea levels to adjust as Earth's temperatures change. As the planet warms, all that new heat energy slowly melts ice caps and glaciers, and eventually, once the Earth stops warming, the oceans find equilibrium at a new level. So if we stopped emitting carbon dioxide today, how much higher would our sea levels rise? Well, we have a pretty good idea of what things looked like thousands of years ago when atmospheric CO2 levels matched ours today. In this episode, we're going to use some amazing new imagery to simulate what places we know and care about would look like in a few different warming scenarios in our lifetime and just beyond. It turns out we don't have to project far into the future to start seeing major impacts on our coastal regions, and that will impact millions of people. Carbon dioxide levels are currently rising faster than at any time since the last ice age. I know that because I went and held 50,000-year-old ice from Antarctica that has tiny bubbles of ancient atmosphere trapped inside of it. Scientists use those bubbles to compare our current atmospheric carbon to the distant past. I was holding that ice while filming a very exciting broadcast season called Weathered Earth's Extremes, which you can stream right now. Scientists at Oregon State University found that we're currently emitting CO2 10 times faster than at any time in the last 100,000 years. If you want to learn what that discovery means for our weather today and see more of Weathered on location around the world, head over to the PBS streaming app where you can watch all 6 episodes right now. And to learn more about sea level, stay right here. Coastal communities are already feeling the impacts of sea level rise, but so far, what we've experienced is tiny compared to what we'll see in the future because the rate of rise is speeding up. In the last 30 years, we've had about 4 inches of rise, but we're projected to see a foot in the next 30. There are a lot of unknowns when it comes to sea level rise, but paleoclimate records show the potential for a startling future.
125,000 years ago and 3 million years ago were some last high stands of sea level that are comparable to when temperatures and carbon dioxide levels were about the same as they are now. And back then, we know that sea levels were 5 meters, maybe 10 meters higher than they are today. So we still probably have a lot of melt left to occur.
Here's what 10 meters of sea level rise will look like in the US, according to the data model visualization tools created by Climate Central and powered by NOAA data. If or maybe when that happens, much of New York, Long Island, and Newark would be underwater. The White House would become waterfront property, along with all of Norfolk, Virginia, Savannah, Georgia, and so many more. But the most impressive change is southern Florida. where major coastal cities would be submerged. In southern Florida alone, more than 10 million people will become displaced. Even in mountainous states like California, much of San Francisco, and even Sacramento would be covered. Worldwide, around 1 billion people, or about 1/8 of the world's population, live less than 10 meters above current high tide lines. Most of the country of Bangladesh would be underwater. All of Bangkok, Shanghai, and most of Hanoi would be covered, as well as much of Singapore, Buenos Aires, and of course, nearly all of the Gulf Coast. Without a meaningful reduction in Earth's average temperature, this is very likely to play out eventually, and that's just at current CO2 levels. As we continue to emit greenhouse gases, the projections rise even higher, but it'll take centuries for sea levels to catch up with current temperature. But what exactly is causing sea level rise?
The dominant signals causing global sea levels to rise are about 2 parts land-based ice melt, Antarctica, Greenland, mountain glaciers, and about 1 part thermal expansion. So roughly 2 to 1.
When water warms, it takes up more space. And there's so much water getting warmer in our oceans that thermal expansion used to be equal to ice melt, but that's changed.
The ice sheets are really starting to lose mass, and that the rate of which they're losing mass is accelerating, and that's overtaken the thermal expansion part. And that's the real elephant in the room, is how much are these ice sheets going to melt, and what will that look like at the end of the century?
Projections for the next 30 years are more dependable than looking further into the future. So we'll start at 2050. Over the last 100 years, oceans have risen about a foot, but that rate of change is increasing.
So history will repeat itself and fast forward. We're set for a foot of sea level rise in the next 30 years relative to 2020.
1 foot may not sound like a lot compared to 10 meters or 30 feet, but low-lying coastal communities around the world will absolutely feel the impacts. And that 1 foot of additional water pushes floods higher as well. So on our US map, we're adding the ground covered by a 10-year or 10% chance flood to our map, meaning the likelihood of this flood happening this year is 1 in 10. Many low-lying coastal communities have levees and seawalls, but on our maps, we're showing areas that are potentially protected as flooded to give a sense of the risk. But what will these sea levels look like on the ground? Enter Climate Central. They're undertaking an ambitious project driving the east and Gulf coasts of the US, collecting images and elevation data to create realistic scientific-based flood model visualizations. We talked to Max, who is out collecting data for this project.
Right now I'm in beautiful Daytona Beach, just woke up. This is Climate Central's Edge of America Flood Rover 2. The vehicle, it's a fully electric Ford F-150 Lightning. Up on top, we have mounted on both sides 2 cinema cameras, and in between those 2 cinema cameras is the silver cylinder. This is a LiDAR unit, which sprays basically a laser cloud, similar to what they use in augmented reality. And then the other 2 units up there are GPS units.
With that data, they can create scientifically accurate images of future sea level.
Our interface allows us to zoom in on a particular city or town or road, like Charleston. So what you're seeing is just based on 3 feet of ground level water. This is what the downtown Charleston market might look like with 3 feet of water.
We'll look at our most likely warming and sea level rise scenarios in a bit, but first, we're gonna look at 4 to 5 degrees of warming, and it's not the most likely path, but if renewable energy transition takes longer than we currently project, it is possible.
If we start talking about 4, 5 degrees C, we're talking perhaps more certainty in saying, yes, we're gonna hit 3, possibly 4 feet, even more.
4 feet would put large parts of the East Coast underwater, and populous global cities like Shanghai and Bangkok would no longer exist the way we know them today. But there are a lot more unknowns the further out we project, and by 2100, melt could speed up. The potential collapse of large ice sheets could be a major catalyst for faster melt.
What will be some of the triggers that might create some collapsing, some rapid discharge? These processes aren't very well modeled. They're not very well observed. Is it plausible by 2100 for global sea levels rise 2 meters. And what would that look like along the United States? Well, that 2 meters would actually look like 2.2 meters. So that would really be like 7 feet, 8 feet. Now that's a very low likelihood. But what if these glaciers really start becoming unhinged? These ice sheets really start to melt.
2.2 meters of rise along the East Coast would be devastating. In Florida, popular cities like Miami and Cape Coral would be flooded. Cities along the East Coast would be completely changed, from Savannah, Georgia, Charleston, South Carolina, and all the way to Philadelphia, New York, and Boston. As we model out to 2150, there are even more uncertainties.
If some of these known unknowns start kicking in at higher temperatures, 4 to 5 degrees C, the numbers just become a bit scary, right? We're talking about upwards of 4 meters of sea level rise, 12, 13 feet. Very unlikely, but we can't take it off the table.
But for now, some good news. Our most likely emissions and warming path shows very significant cuts in greenhouse gas emissions by 2100, hitting somewhere around 3 degrees, hopefully just under.
On the trajectory that we are on, let's say 2.5, 3 degrees C rise by the end of the century, we're looking at somewhere about probably 3 feet of rise on average along the United States coastline.
And that extra foot is meaningful compared to the 4 or 5 degree warming scenario with 4 feet of rise. And by 2150, well, it's important to understand that we're not currently on track to fully stop warming by 2100. The more we warm in that extra 50 years, the faster seas will rise.
The coastal environment is going to look very different regardless of what we do. We're on a trajectory now of 6 to 7 feet by 2150 under the commitments at hand. It could be a lot larger, probably not going to be too much smaller.
So by 2150, our grandchildren and great-grandchildren are very likely to witness the evacuation of large parts of New York City, most of Miami, and the already below sea level city of New Orleans, plus dozens of smaller towns and coastal communities, just to name a few. And that's in a relatively optimistic scenario. I want to talk about Louisiana for a second. Much of the area is already below sea level. There are over 3,000 miles of levees protecting large parts of the area, including New Orleans. So will all cities just build walls instead of relocating as our seas rise? Probably not, but it's hard to say. Levees are only protective up to a certain point, and as seas get higher, the risk of failure becomes catastrophic. We have already seen government relocation projects for communities in Louisiana where the government pays to move an entire community, often because it's cheaper than extending a levee or constant rebuilding. Isle de Jean Charles is a community we visited while producing Weathered Earth's Extremes. It was relocated after it was excluded from a levee project, but the choice to leave was still incredibly difficult. And even with effective levees, eventually communities will be living in a very risky fishbowl.
The Texas spine, this idea of big gates in Boston and New York City, that's not going to combat sea level rise, I'm sorry to say.
But we have the technology to reach net zero. And that's the point when we have reduced human greenhouse gas emissions to a point so low that we can capture the rest and put that carbon in long-term storage. And we can reach that point far earlier than 2150. If we really move quickly and support the energy transition, we could reach net zero well before 2100. That will mean a lot more support for speeding up the transition to low carbon energy like solar, wind, batteries, electric vehicles, and even our food systems. To learn more about the transition and the impacts of warming right now, check out our new broadcast series, Weathered Earth's Extremes, on the PBS app. Is your home covered by water on any of these maps? If so, what's your plan? Let us know in the comments, and see you next time on Weathered. Most of the deadliest heat waves to date have been dry heat waves, but as our climate warms, a possibly even deadlier heat is on the rise.
It doesn't matter how breezy it is. It doesn't matter how much shade you're under. It doesn't matter how much water you're drinking.
These are extreme humid heat waves, often referred to as wet bulb events. And these are, in my opinion, one of the scariest byproducts of climate change. They've been relatively rare historically, but a new study shows that by 2 degrees Celsius of global warming, many of the most populated places on Earth are likely to experience them. And the only way to protect ourselves from these dangerous wet bulb temperatures is to cool our environment. But what happens if that's not possible?
The time of year that always has the highest stress on the grid is always just the hottest day of the year because so many people are using AC. And so then the AC is liable to go out.
What happens if there's another extreme weather event, if you have a tropical cyclone that comes in, wipes out power?
Stick around as we break down why these temperatures are so deadly and how we can prepare for a world that's so warm our bodies literally can't handle it. Let's start by talking about dry versus humid heat. Dry heat waves are usually driven by large high pressure systems that trap hot air near the surface. These systems push air downward, and as the air compresses, it heats up in a process called adiabatic heating. If the high stays stuck in place, the heat builds day after day with no clouds or wind to carry it away. And that's exactly what happened during the 2003 European heat wave and the 2021 Pacific Northwest heat dome. Now let's take a look at humid heat.
As temperatures rise, we can hold a lot more moisture in the atmosphere. And so this means that if a given location has air temperatures going up with ongoing climate change, it's likely that if they have a moisture source, humidity is also going to increase.
We just saw how dangerous this can be in 2015 when one of the most extreme humid heat events on record struck Karachi, Pakistan. Temperatures up to 45 degrees Celsius combined with oppressive humidity. Power outages and water shortages made conditions even worse. At least 1,200 people died in just 10 days, most from heat stroke and dehydration. Humans primarily cool down by sweating, but when the air is humid, sweat can't evaporate as easily, so we don't cool off as well. This is where wet bulb comes into play. Wet bulb temperature combines heat and humidity into a single number, which helps us understand when conditions become dangerous or even lethal.
You can imagine taking a normal thermometer. If you take that thermometer and you cover the bulb in a little sock that is then placed into a container of water, so it's constantly wetted, evaporation is going to take place off of that little sock, and it's going to have a net cooling effect.
The wet sock at the end of the wet bulb thermometer functions similarly to human skin. Water evaporates off the wet sock, while sweat evaporates off our wet skin. In both cases, evaporation carries away heat into the surrounding environment.
But the more humid the ambient air is, the more difficult and less efficient that evaporation is to take place. And so that makes any cooling through evaporative cooling less efficient at high temperatures and high humidity.
Which is why humid heat feels so muggy and uncomfortable for us, and why it can be so dangerous. There have been a number of attempts to better understand how humid heat affects the human body, in particular, where our physical limits are. But it's not easy to identify dangerous wet bulb thresholds because, well, they're dangerous.
So obviously you can't put someone in a heat chamber and truly cook them. That would be unethical. But what you can do is increase temperature and humidity and measure someone's core temperature and see what's the point at which their core temperature starts to increase. And that's the limit of compensability.
The human body generally does a good job of regulating its core body temperature through sweat. But once we cross the limit of livability, or compensability, as scientists call it, our core body temperature starts to increase uncontrollably. And this wet bulb temperature range is actually a lot lower than we previously believed.
So this paper is really trying to summarize the most state-of-the-art estimations of these thresholds. And so what we see is that there is a range. So uncompensable wet bulb temperatures range from about 19 to 32 degrees Celsius.
And you might think the lower end of this range, 19 degrees Celsius, sounds really low, but it's important to understand that a 19-degree wet bulb does not equal 19 degrees on a regular thermometer. So 19 degrees Celsius wet wet bulb is actually more like 46 degrees Celsius with low humidity or 32 degrees Celsius with higher humidity. And the reason there's a range is because this threshold depends on a number of variables, including activity level, exact air temperature and humidity levels, and age.
Older adults' thermoregulatory responses are worse. They sweat less efficiently. They also have higher risks of comorbidities, so things like cardiovascular and respiratory diseases.
So according to their study, where on Earth are we likely to cross these thresholds? Well, at 2 degrees Celsius of global warming, which could come in as little as 2 decades, for older adults, it's about a third of Earth's land area. But that only tells part of the story.
It's 35% of the land area, but it's also many of our most populous places on Earth. Most of India, most of the populated area of China. This is most of the eastern portion of the U.S.
And if we let global warming get really out of hand, or if climate sensitivity is just on the higher end of our projections, at 4 degrees Celsius above pre-industrial levels, over 60% of Earth's landmass could see these dangerous wet bulb temperatures. Heat is the deadliest weather disaster in the U.S. and many parts of the world, and it's projected to get a lot deadlier. During the 2003 European heat wave, up to 3,400 people died in Paris alone. At 2 degrees Celsius, which is, again, only a couple decades away, scientists found that Paris will see deadly heat waves like this once every few years rather than once a century. And though this heat wave in 2003 was among the deadliest in recent history, it didn't get close to the dangerous wet bulb thresholds we've been discussing in this episode. But the 2015 heat wave in Karachi did. It passed the uncompensable wet bulb threshold for older adults for something like 8 to 10% of the time. But at 2 degrees Celsius of warming, we can see that the uncompensable threshold is crossed for younger adults as well. And at 4 degrees, models show that the same event would cross the uncompensable threshold for older adults for about 90% of the heat wave's duration. And the thing to remember about these critical wet bulb thresholds is that once you cross one, the only way to bring your internal temperature down is by cooling yourself or your environment.
It doesn't matter how breezy it is. It doesn't matter how much shade you're under. It doesn't matter how much water you're drinking. The only way you can protect yourself from these conditions is by cooling your environment. And so that is why air conditioning is really the major adaptation measure and protection measure that we have.
And although AC is one of the most important tools for surviving extreme heat, it's far from perfect. First of all, it's expensive. AC is energy intensive, and as our climate gets warmer, many people won't be able to afford to stay cool. And due to its financial inaccessibility, many people in places most vulnerable to deadly heat don't have access to AC. Second, air conditioning doesn't eliminate heat. It just moves it. Cooling the indoors means transferring the heat outside, which warms the surrounding air. And in cities, this added heat can worsen the urban heat island effect. Now, let's imagine that everyone could afford air conditioning. It still wouldn't automatically solve the problem. Our power grids in the US and globally weren't designed for everyone to crank up their units at once. During heat waves, widespread outages become more likely, leaving the most vulnerable at even greater risk.
If AC units were our only way of protecting people, as soon as the power system fails, whether that's from the grid being overloaded or if we have another weather-driven sort of infrastructure damage, that's going to put people immediately at risk.
And these compounding hazards, like a heat wave after a hurricane, are a growing concern as we head towards unprecedented levels of warming for humans and as weather across the board just gets more extreme. But there's one more catch. The more we rely on AC, the more we could be fueling the base problem of global warming.
If you tried to just build out air conditioning to deal with heat risk, how much would that contribute to carbon emissions across the world, and how much would that positively feedback on global temperature, making the temperature even higher.
Right now, air conditioning accounts for about 3% of global greenhouse gas emissions. And according to the International Energy Agency, the number of AC units worldwide is expected to nearly triple by 2050, leading to a massive rise in energy demand. So what do we do about this paradox? Well, I think it's a powerful argument for transitioning as quickly as possible to clean energy. The only way to meet the growing need for AC without accelerating climate change is to power our grids with renewables. And of course, there's a lot we can and should do beyond just air conditioning. We can rethink the design of our cities by installing white or green roofs and planting trees. We can also build more cooling centers, upgrade our electrical grids to be more resilient, and prioritize protecting the most vulnerable during heat waves. The truth is that we are headed into uncharted territory, but it's also true that we still have time to choose how bad it gets. So, do you live in an area that's already experiencing dangerously hot and humid conditions? What strategies have worked for you to handle the heat? Let us know in the comments, and we'll see you next time on Weathered.